Alrighty, well, let's go ahead and take a look at some of your questions here. I'm going to turn off that fan because I realize it's probably distracting in the background. Okay, that should turn off. Okay, so let's take a look at some of your questions. So Miriam had a question: how and when we include wedge and dash. So wedges and dashes, if I can spell, these are for tetrahedral electron geometry. And I did have a question about telling the difference, and we'll go over that. So we'll do that. So when we're looking at something like methane, its Lewis structure is pretty simple, right? This is a 2D structure, but the tetrahedral shape is actually three-dimensional. So we use wedges and dashes to kind of just show this. We display it using 3 dimensions and having better bond angles, because those bond angles look like they're 90 degrees, right? But we know that tetrahedral things should be 109.5. So we will just choose any 2 of our things to be on wedges and dashes. It doesn't matter which one. We're going to put one on a wedge, one on a dash. The wedge means that it's pointing towards us, and the dash means it's pointing away from us as we're looking at it. So it brings it into 3 dimensions. And even if we have a lone pair on something, so say like ammonia, we would still need to do wedge and dash if we really wanted to show it in 3 dimensions. This helps us see that this has got to be that trigonal pyramidal shape. So we're looking at these just to show us 3D shapes of things. I don't really focus on this too much in this class. If you're going to take 111, then yes, we'll focus on this more. And in OChem, this is all we do with wedges and dashes. It's just how we just kind of have a formal way of going from, I don't think, sorry, Martha, I think my screen isn't showing. Here, let me try this. Okay, let's see if that works. And so we're looking at this, and so that's why we're going to use wedges and dashes. So it's just for showing 3D, because in reality those molecules are 3-dimensional. So not really something to worry about in this class, but just be aware that this is the convention we use in higher up chemistry. Okay, so we'll do that. Okay, but for now, I am totally cool if you leave your stuff as the molecules on the left. You're good to go there, so no problems. Alrighty. Let's see. So Erin wants to do difference between molecular and electron geometry. Yes. So the difference between molecular and electron geometry. Alrighty. So, electron geometry allows us to set the shape for everything that's on our central atom. Excuse me. I suppose I can write that. So electron geometry kind of, it's the shape of everything around the central atom. And so anything that's tetrahedral it could have a whole bunch of different types, right? As long as we have 4 things, any of these kind of families of compounds are tetrahedral in terms of their electron geometry. So any of them, I'm just going to do 2 because why not? Anything that has 2 or 4 things on it, no matter what those things are, so I'm kind of drawing bonds to the lone pairs just so we can see that there are indeed 4 things on it. So tetrahedral things, this is the electron geometry. These are all tetrahedral. And so this sort of structure is just to show us what they all look like, the similarities between all of them. So anytime you have 4 groups, it's always going to be tetrahedral. Anytime you have only 3 groups, it'll be trigonal planar for electron geometry. The difference is we're going to see that lone pairs are not visible to us. They're incredibly small. Atoms are much, much bigger than lone pairs are. So that's the reason that we will talk about molecular shape as something different. So let me just write that out. Because lone pairs are so small, we can't really see them. We have a hard enough time seeing atoms as it is, but there's no way for us to see electrons. Because remember that atoms are 10 to the 15 times as big as electrons are. So huge, huge, huge difference in size. And so as a result, we will, anytime we have a lone pair, it's important for us to look at what it looks like even without that lone pair there. So when we look at ammonia, for example, we might think, okay, if that lone pair is not there, well, then it's just trigonal planar, right? But that's just not the way it is. Experiments show us that this angle, which would be 120 degrees, is not real. This is not reality. Oops. In reality, we end up with, I'm going to use the wedges and dashes here, we end up with angles that are just a little bit less than 109.5. And so that's why it's important for us to talk about molecular geometry as well. Because even though we can't see that lone pair, we still feel its presence, its influence. The lone pair still dictates to us the bond angles. So it's still tetrahedral if we count everything, but molecular shape is going to be different. Because if we look at this, this is not a tetrahedral substance. We don't have another hydrogen or something up there. We don't. So we have to have a different name for it. And so we need to remember then that any time we have a lone pair on the central atom, and I think this was your question, Martha, this is when your molecular shape is different from the electron geometry. So that's when. So you're absolutely right that the Lewis structure and molecular geometry kind of look the same, and sometimes they're the same and there's no difference, right? Totally common, right? But the difference is that you're going to have a different shape and a different name of the shape, therefore, if you have a lone pair on your central atom. So that's going to be what tells you, right? And so if you can classify anything under those categories, AX4, AX3E, whatever those are, anytime you have an E in your kind of family of shapes, that's when your molecular shape will be different from your electron shape. Does that kind of make sense, Martha? And just so you know, when we're drawing the Lewis structure, very often we don't draw the shape. Very often we'll still draw just a plain Lewis structure. So it's normal for us to still draw ammonia as this. We still will draw it like this as a Lewis structure. This is 2D. This is 3D. So it just depends what we are looking at here. So Martha, just so you know, you are muted. So if you do want to say something, man, my internet is still crappy. Like, I'm looking at it, it's not doing so well. If you do want to say something, like, if this is unclear still, we can look at that. So, and then Aaron, since you're here, go ahead, Martha, if you have anything.
I don't know how to unmute. Hello?
You're good. I can hear you. Yep. Mm-hmm.
Okay. Yes, I understand now. So yes, that's exactly what I meant. And I was doing those sketches and also adding the one because I wasn't sure. I was adding those two and then one and creating the little bubble shapes just to be safe. But yes, I get it now.
Okay, yeah, totally. Normally we write them like this. So this is the easiest way for us to do it. And yeah, the bubble shapes definitely would take a lot more time and they look a little clunkier, right? So just in the interest of keeping things clean, we usually just draw the 2D for sure.
Okay, so, well, thank you.
Okay, so Aaron, we kind of just went over yours as well. So the difference between molecular geometry and electron geometry, it only changes when we have a lone pair on our molecule. Because lone pairs are so small, we don't see them, but we do see the shapes afterwards. We can still predict these bond angles. And the bond angles do work. So even though we don't see the lone pair on ammonia, if the lone pair really wasn't there, we would have 120 degree bond angles. It would just be trigonal planar. But the lone pair is there because our bond angles in reality are just a little bit less than 109.5, which tells us that this is something that comes from tetrahedral. And the rule here is that anytime you have a lone pair on your central atom, that's when your shape, your molecular geometry and electron geometry are different. And so it's just a matter of consulting kind of that chart that I gave you guys, where it's like this one would be trigonal pyramidal. Because it's AX3E, sorry. So because of that lone pair. So there is going to be some correlation of recognizing these patterns of when we get certain molecular shapes. It's all just dependent on how many lone pairs we have on our central atom. All right, so if it's 0, your electron and molecular are the same. If you have one lone pair, that'll change it. If you have two lone pairs, it changes. Any number of lone pairs, you'll change your geometry. So there is that difference there. Okay, and then let's see here. On exam 2, explain the answer. It says the electron configuration chloride ion should be this, but the answer is aha. Okay, gotcha. So this one's kind of a trick question, Aaron, and I gotcha. So what's written here is chloride ion. Right? Compare this with chlorine. Chloride has 18 electrons. Chlorine has 17 electrons. Right? Remember that things will form ions in order to become like noble gases. So the chlorine has gained an electron and therefore is now chloride, the chloride ion. So it has gained an electron. So you're absolutely right for chlorine. I'm going to write your electron configuration here. This is for chlorine. 17 electrons. If we have chloride, which was the trick part of this, we're adding an extra electron, right? Which then brings us to, we would add that to the P, right? Because that's the only other spot we have left. And this is the same thing as argon. So that's why.
I think you froze.
I froze. I know my internet is being really bad. I need to go like replace my router or something. I've had trouble like from Wednesday onwards. Um, don't worry though, the one that I put on YouTube afterwards will be hopefully okay. So even though I know I'll probably be like weird sounding, I'll probably cut off here, or if I might freeze. That's pretty normal. Has it caught up, Erin?
Yes, I finally see. I see your.
Okay, cool. Yeah, I don't
image.
know why my
And that
internet's
makes sense.
crappy. So yeah, so that was the trick. There was that it was chloride, not chlorine. So just a trick with the name there. Okay, and I think Miriam had another question. Oh, but hers was just very basic. Okay, never mind. Do we have any more to go over here? Let's see. Okay, we got through the wedge and dash, talked about the difference between the geometries and the electron configuration. Is there anything else any of you would like to go over?
Can you define the abbreviations that you used during the geometry? What does the A and the X stand for?
Oh, sure. Okay. Yeah, we'll do that. And then Martha, I know you wanted to ask, and we'll get you after this. Cool. So, these things. AXE notation. A just means your central atom. And for this class, there's only ever going to be one of those. So it'll just be A. Just leave it like that. X is the number of atoms connected to the central atom. And then E is the number of lone pairs on the central atom.
That was the piece I was missing, and that's why I could not figure it out. That
Oh.
makes so much more sense.
Oh, okay,
Thank you.
good. I don't remember how I explained it last time, so let's just do a couple just for fun. I'll give you the Lewis structure. This one would just be AX3. If we look, this carbon has 3 other atoms connected to it. It's got an oxygen, it's got a hydrogen, and then a second hydrogen. Doesn't matter that there's double bonds. Doesn't matter that the oxygen has lone pairs. No lone pairs on carbon, only 3 outer atoms. This thing would be AX3. If we look at water, central atom is oxygen here. So it has 2 outer atoms and 2 lone pairs. So this would be first outer atom, our second outer atom. This would be our first lone pair and our second lone pair. And so we would define this one, or classify this one as AX2E2. Okay, so that's how we would put this into practice. All right, Martha, let's go for your question.
No, I didn't have a question. I said I was good.
Okay, sorry.
Just so far, it seems like I've been okay.
Good.
Other than that, I don't have any questions.
Great.
I hope I don't have a bunch of questions as soon as this thing is over.
Well, even so, you can always like write them out, and I'm happy to give like kind of written explanations. So even if that might help a little bit less, but at least I can help you out still a little bit. So if things come up. All right. I think Aurora typed in the go over the periodic table configuration method. Okay, sure. Sorry, Aurora, I didn't see that it was in the other channel. Okay, so periodic table configuration method. All right, let's choose a nice atom here. Should we go completely crazy, Aurora? Do you want to go like a complex one? Something later on, like a higher atomic number, or do you want to start with something a little bit easier? You are muted, by the way, Aurora, just so you know. So, there is a button in the bottom left that looks like a little microphone. That's what you would want if you want to unmute yourself. But if not, that's totally cool. You do not need to talk. So, here, why don't we do tin, number 50, right over here. Okay, so I'm gonna go ahead and just switch back here. Okay, so tin is somewhere over here. It was in period 5 of the periodic table, and I think it's in the second of the P block. So that's group 14, yeah. So, first thing we want to do for any time we're doing the electron configuration is to figure out what our last electrons are, right? This is the P block that we're in. I'm going to erase this. Remember, there's 6 columns in the P block. That tells us the number we're going to have at the end. So we are in 5p2 as our final electrons. So that's where we need to end this thing, right? So we found our element on the periodic table. We see what period it's in, what column it's in, and which block it's in. And so this one will be in 5p2, will be its last electrons. And we can kind of do this either reverse or going forward. I'm going to erase tin right now, so we can remember this was 5p. Above it is 4p, 3p, and 2p. I'm going to actually move this line a little bit down as well because I think we need just a little more space there. Yeah, that'll help. Remember that the D block is there transition metals. Everything there is one less. So this is 3D. This is 4D here. So these are all in the same row of the periodic table. So just remember the D is always one less than the rest of everything. Here we have 5s, 4s, 3s, 2s, 1s. And so once we have all of these on our periodic table, it's just a matter of filling in everything. So we're going to start here at 1s. We filled all of these always to their maximum capacity, right, until we get to the end. I may or may not need to erase that and move it over because we'll just see how much space we have. So 1s gets us through helium. Now we're over here. So we're going to go through 2s. So that'll be our next one. Now we're over here. We're going to keep going across the periodic table until we get to tin. So that'll be 2p. We've got to fill that one up. Next is 3s, followed by 3p. Now we're over here at 4s. Now we're at 3d. So we're going to put all 10 into 3d. I'm going to erase our 5p2 for now, just because I'm going to run out of space. We're here in 4p, so we're going to have to fill that one up next. Next, we're in 5s. And then we're in 4d. And then now we're in 5p, and that's where we need to stop at 5p2. So this is the only one that's not filled. So everything else is filled to its maximum capacity. And remember, for S, that's 2. For P, that's 6. For D, it's 10. And F is 14. We don't really deal with F very much, but if we had to fill the F orbital, it would be 14 electrons. So remember these magic numbers, I suppose, because those will help us to remember how many of these are the maximum capacities. And then remember that everything full is going to be have its maximum. If we wanted to do this as the noble gas, we would say, aha, we have a noble gas here. We're in period 5, so we're going to look at the noble gas in the row above it. Let's swap over back to our periodic table. So we're looking at tin right here. So we're going to go one row up and find the noble gas. Aha, that's krypton. So if we wanted, we could just say krypton for all this stuff underlined by green. So krypton 5s2 40 10 5p2, and that would be the only thing there. All right. So that's how we use the periodic table to determine the electron configuration. So we need to find out where we are ending, and then we just need to remember which orbitals are corresponding with which like kind of rows on the periodic table. And that's how we would do that. Okay? Alrighty. Is there anything else you guys would like to go over?
No, I'm good now. Thank you.
Okay.
I'm okay. Thank you.
You're good? Okay. Awesome then. Well, I will stick around. Just at me if you need anything. If, in the next half hour or whatever, you say, oh, wait, I do want to do this. Just let me know. And we'll go from there. So, okay. I'll go ahead and I'll pause the recording.